Hey everybody, happy Thursday. You are almost to the end of the week, and we've only got a reminder, we just got a couple weeks left in the quarter, and then we are actually done. We are done with chapter 4 on the beginning of integration, and we're going to expand on integration. Integration is going to be chapters 5, 6, and 7. We're not going to get away from it, but we are going to look at applications of it and do it in a few other contexts. Chapter 5 is kind of a weird mix. I'm not quite sure why the book ordered things the way that they did. But they decided to hold off on exponentials and logs until chapter 5. Now, I do know why they did it. But in general, when this is your first exposure to derivatives and integrals, it's usually a whole lot better to see this with all the other derivatives and integrals. I've sort of thrown exponentials and logs in as we've done derivatives and integrals, but we're going to kind of make sure that you got them solid. So most of what we're going to do here is actually review. There's going to be a couple things that are new, but not really. So this should feel fairly comfortable, hopefully. And if it doesn't, it should be solidifying stuff that you didn't feel comfortable with earlier. So not a lot of the stuff in particularly this the sections we're going to go through today. So section 5.1 through 5.5 is on exponentials and logs. Then we're going to kind of skip around a little bit. On Monday, we're going to look at section 5.8 and 5.9, which is on inverse trig functions, which we've already talked about some, and we've talked about how to differentiate and go backwards on integration. We're going to review that as well. We'll look at some additional problems there. And then we'll go back and we'll look at a couple of very specific things in section 5.6 and 5.7 on something called differential equations, which we haven't really talked about, but is a very useful topic, and it's very much related to derivatives and integrals. So we'll talk about that, and then we'll skip forward to section 5.10, which is on hyperbolic trig functions, which you probably haven't ever seen before. They're not all that weird, but it's another category of function that you definitely need to be familiar with, having come through calculus. So again, today is mostly review. There's a couple of new things that we're going to do, but for the most part, it's just getting our feet under us, remembering some of the derivatives, but particularly the integration techniques that we've had, and applying those in the settings where we have exponentials or logs. Okay. So the first thing that I want to do here is just review a couple of different things here. First of all, there's 4 functions. Well, there's actually 5, but I'm going to start with 4. There's the a to the x function, the e to the x function, the natural log function, and then the log base a of x function. So the first thing that I want you to think through is, the thing I want to review here is, first of all, what was our definition of these? What did they look like as a graph? What did the graph of these look like? Okay. Then what's the domain? And then what's the derivative? And then how do we reconstruct that as an antiderivative? Okay. So let me explain what I mean here. Okay, so the definition of a to the x, well, we didn't really have a good definition here. So if I had like 2 to the x, we talked about what does 2 to the third mean. That's like 3 copies of 2. What does 2 to the 1/2 mean? This is the number that if I square it, I get 2. Okay, so we really didn't have a good definition here, but we kind of have intuitively, we understand exponentials by taking a number to another number power, meaning I need that many copies of that multiplied together. Okay, 2 to the 5th is 5 copies of 2 multiplied together. We kind of have an intuitive notion of this, but we don't have a rigorous definition here. And that's actually the problem. That's why the book waits to present these until later. We'll talk about that later. So really don't have a good definition here. For e to the x, do you remember how e was defined? This is the function. This is the number that I stick here so that the slope at 0 is 1. Okay, one of the things that we talked about, I'll go ahead and graph these. A to the x generally looks like this. That's if a is bigger than 1. If a is less than 1, then it actually, if a is between 0 and 1, it actually looks like that. E to the x looks the same. But the slope right here, I didn't draw this very well, but the slope here is 1. E is a special number so that the slope here is 1. 2 to the x actually has a slope of about 0.7. 3 to the x has a slope of about 1.2, I think. So e is this number between 2 and 3. E is actually 2.71828, etc. This number between 2 and 3 where the slope of the e to the x function is actually 1. Natural log, then, is the inverse of e to the x. And we talked about how to get an inverse. You basically draw the line y equals x and flip. So the natural log function looks like this, right? And then log base a of x is the inverse of a to the x. Okay, and that one looked like, again, okay, this is e to the x, natural log of x, log base a of x. Is this bringing back memories? Remembering these things? Okay, again, to get the inverse function, we flip around the line y equals x, just as a reminder. And in order for this to be a function, this original thing, we used to talk about how it needed to be 1-to-1. I'm just pulling these words out so you kind of remember this. Okay, the domain of a to the x, notice I can plug in any number, so the domain is all real numbers. Same for e to the x. What's the domain of natural log? 0 to infinity. Not including 0, right? You can't plug 0 into natural log. Same for log base a of x. Okay. Good so far? All right, the derivative of a to the x is a to the x natural log of a. And the derivative of e to the x is actually e to the x. It's actually e to the x natural log of e, but the natural log of e is 1. That's why we don't write it. And that's why that's my favorite function. Derivative of the function is itself. Derivative of natural log, do you guys remember this? Is 1 over x. And the derivative of log base a of x is 1 over x times the natural log of a. Natural log of a goes down on the bottom. Okay, for a to the x, the natural log is right next to it. For log base a of x, it goes down on the bottom. Okay, flipping that around, antiderivative laws, the antiderivative of a to the x is actually a to the x over natural log of a. Don't forget your plus c if we're talking about a general antiderivative. The antiderivative of e to the x is just e to the x. Okay. Now for the antiderivative of 1 over x, the thing that perturbed us about this was that 1 over x actually has a domain of everything except 0, but that's not the domain of natural log. So then what we did was we threw in a fifth function here. This is the fifth function that I warned you about, which was the natural log of the absolute value of x. And what that looks like, it looks like natural log, but natural log copied, flipped over onto the other side. This has a domain of everything except 0. And what we saw before was that its derivative is actually also 1 over x, just like the derivative of natural log. I'm not going to prove that here because we've done that a couple times. And so now, what we like to do is if we have a 1 over x dx, if we're finding the antiderivative, we want the most general one, so we want the one that has the same domain, and so we use natural log of x, natural log of absolute value of x there to capture that. Okay? So those are our those derivatives and antiderivatives. Okay. All right. So with that in mind, I'll just copy these antiderivatives because we're going to be working on antiderivatives today. Okay, so let me erase this now. And we're just going to do a bunch of problems. But they're harder problems. Well, some of them are easier, some of them are harder. Okay. And a lot of them are going to involve, some of them will involve substitution, some of them will involve other techniques that we've used previously. Okay? So let's do a couple of examples here. Let's do the antiderivative of 1 over 4x minus 1 dx. Okay, the first thing that you should notice is that this looks a lot like 1 over x, except instead of x, I have this other thing in here. And whenever I say instead of x, I have blah, that usually means composition. And composition is usually a sign that I need to do what technique here? I need to do substitution. So let's try substituting. U equals 4x minus 1. And so du is going to be the derivative of all this is just 4 dx. And if I bring that 4 over to the other side, 1/4 du is dx. So now what I'm looking at here is 1 over u, and then I've got a 1/4 du. That 1/4 just comes out of the integral. And then the antiderivative of 1 over u is just natural log of absolute value of u. Please make sure you include that absolute value, and please make sure you include the plus c. Do not forget that. And then we just sub back in. 1/4 natural log absolute value of 4x minus 1 plus c. That is my answer. Okay? We good? All right, any questions? Let's do another one. Let's do the antiderivative of x over x squared plus 1 dx. Okay. One thing that you'll notice here is that this top part, suspiciously, x dx, looks like the derivative of the bottom. That's also another indication that we need to do substitution sometimes. That was one of our more difficult examples of needing to do substitution, right? So I'm going to try that here. U equals, let's do u equals the bottom, and so du is 2x dx, but I only need the x dx, so let's put the 1/2, let's put the 2 on the other side, make it 1/2. Okay, so then what I'm looking at here, the x dx on the top becomes 1/2 du, and the bottom is just u. So again, that 1/2 comes out, and I've got 1 over u du, which again integrates nicely to a natural log. And now I just need to throw that other piece back in. Natural log of absolute value of x squared plus 1. Sense. The trick here is catching that I need to do a substitution. That is the tricky part to this problem. Okay. One thing you will notice if this problem actually came in the chapter and there were answers in the back of the book, you may see parentheses here instead of an absolute value. One thing I just want to point out here is that x squared plus 1 is always positive, so it doesn't matter if you take absolute value or not. So in certain cases, they'll drop the absolute value, but it's only when the function inside is positive anyway, so you don't need it. You need it in this case. Okay. All right, let's look at another example. Let's do the integral of x squared plus x plus 1 over x squared plus 1. Okay. Now, we are going to tackle these kinds of problems in much more generality when we get to chapter 7. However, when you see a polynomial over a polynomial, okay, you'll notice that this is a polynomial over a polynomial, and the top polynomial has a degree, in other words, the highest power of x, that's equal to or bigger than the bottom one, there's a technique you need to do first. And again, we'll do this more in chapter 7, but I want to introduce this here. The technique that you need to do is what's called long division of polynomials. And you're going to be like, oh my goodness. It's been a while since I've done long division of polynomials. That's okay. We'll just review it real quick here. Like I said, we're going to do it more later on. But I'm going to take the top polynomial, x squared plus x plus 1, and divide by the bottom polynomial. Now, whenever you do this with polynomials, you generally, if there are certain terms missing, like on the bottom there's an x missing, I'd usually write 0x. Okay? And then what I do is I say, okay, what do I need to multiply this thing by to get the first part, x squared by, to get x squared? And then in this case, I need to multiply by 1. So I'm going to take 1 times this thing, so 1 times x squared plus 0x plus 1, and I'm going to subtract them. Is this seeming familiar? Okay, x squared minus x squared is 0. X minus 0x is just going to be x. And then 1 minus 1 is 0. So what's left over, this is the part that's left over. Once the power that's left over here is less than the top power here, you're actually done. And what this quotient ends up being is 1 plus a remainder. The remainder is x over what's left here, x squared plus 1. Okay. Don't get too hung up on this. I'll do, there are 2 examples like this on the homework, and I'll actually do them in class. I'll do them in the lecture. So if you're like, oh, I don't remember how to do this, that's okay. But the point is that we're going to take a polynomial over a polynomial where the highest power here is equal to or bigger than the highest power here, and we're going to get it into a form now that we can actually work with it. And you'll notice now I get the first, this 1 here, I can get the antiderivative of that, and this other part is exactly this integral here, so I'm just going to copy, rather than redo all that work again, I'm just going to copy that answer there. Okay. So again, if the highest power of x on the top is bigger than or equal to the highest power of x on the bottom, then the first thing that you do is long division of polynomials. And there's some more explanation of this in the book too, so I can kind of refer you to that. All right. Okay. Let's keep going. I'll warn you that my computer's about to die and I do not have a power cord here. So I'm going to try to get through as many of these examples as I can, and we'll see how things go. So let's do now the integral of tangent. You know, I actually told you last time what this was, but it was a really weird answer. And I hinted that substitution was where you could get this. But we're actually going to do it here, all right? So tangent, if I wanted to integrate tangent, I don't have a nice just formula for it. But if I turn tangent into sine over cosine, one of the things that I notice is that if that top part, what did I do with there's my red marker. If the top part is the du, then this bottom part is actually the u. So if I let u equal cosine, then the du is negative sine, but that negative is not a problem. Okay, so substituting back in, I get negative sine of x dx is negative du, and the bottom is just u. So the antiderivative of 1 over u is natural log of absolute value of u. And then I sub back in cosine of x. That was actually the answer that I gave you before. So that turns out to be the answer here. Okay. One thing I want to point out here is that I actually want you, there aren't too many of these that I want you to memorize. This is going to be one that I want you to memorize, and I'm going to try to summarize this. But tangent, the integral of tangent is actually this answer I want you to actually memorize. We're going to use it later. So I'm going to start to harp on that. And that's something, again, the way we did this before is to memorize, throw things on index cards and memorize them, okay? In a similar way, the antiderivative of I don't want you to memorize the antiderivative of cotangent. You can actually derive it in the same way. It turns out to be the natural log of sine, but there's no minus sign out here, so the derivative of the cofunction kind of gets rid of the minus sign there. All right. Since we're doing antiderivatives of trig functions, we know how to do cosine and sine already. We now know how to do tangent and cotangent. Cotangent you would just turn into cosine over sine and do u substitution. Since we've done those, let's go ahead and do secant as well. Okay. And for secant, and I would never expect you to actually remember this, but I'm going to use this so we can get the antiderivative of secant. To do secant, somebody actually came up with a trick. I'm not going to tell you where they came up with this trick. There's actually a way that you can come up with it. But what they thought was, okay, I'm going to actually multiply by a fraction, and that fraction is going to be 1. But it's going to be secant x plus tangent x over secant x plus tangent x. You might think, why in the world would somebody do that? I'm not going to answer that right now. But the thing that I want you to see, if I do this, if I multiply the top out, I get secant squared plus secant x times tangent x. And on the bottom is secant plus tangent. Does anybody notice anything? I'll let you finish writing for a second. Does anybody notice anything about the bottom and the top, the relationship between those? This is where the trick comes in handy. Notice that secant squared x is actually the derivative of tangent, and secant x tangent x is actually the derivative of secant. So if you let u equal the bottom, it turns out that the top is actually cooked up to be the derivative of the bottom. Isn't that crazy? It just happens to work that way. So what you end up with here is simply 1 over u du, which is going to be the natural log of absolute value of u, and then we just sub back in. Okay, so the antiderivative of secant is the natural log of the absolute value of secant x plus tangent x. And again, this is another one that I want you to memorize. So I want you to memorize the tangent one over here. There's actually 4 trig functions that we didn't, as of today, know how to anti-differentiate. I want you to memorize 2 of these. The tangent one and the secant one. Put these on index cards and memorize them. It will come in very handy later, so please do that. I'm not joking here. And then the other ones you can actually get by just changing the antiderivative of cosecant is natural log of cosecant plus cotangent, except there's a minus sign here. So they kind of make sense, just like the derivatives of secant and cosecant were related, the derivatives of tangent and cotangent are related. If you memorize these 2, tangent and secant, you can figure out the other 2 pretty easily. Okay? All right. So please, please, please memorize those. So we actually now have the derivatives of all of the trig function. The antiderivatives of all the trig functions now, which is nice. Okay, let's do a couple of examples involving e to the x, just to get those under our belt. And then we'll see how much time we have left here. So let's do the antiderivative of x e to the minus x squared. Okay, so again, what you might notice is that I have a composition here, and then this first thing is kind of the derivative of the second thing, so I'm tempted to let u equal negative x squared. And then du would be negative 2x dx, so that x dx would be negative 1/2 du. So coming and substituting in, I'd get e to the u, and then I'd have a negative 1/2 du here. So if I pull that negative 1/2 out, I've got e to the u du, and the antiderivative of e to the u, that's my favorite function, it's just e to the u. So this ends up being negative 1/2 e to the minus x squared, subbing back in. Make sure you do not leave those problems just in terms of u. You need to sub back for x. Okay. Okay, let's see if we can get through 2 more examples before my computer says goodbye. Let's do e to the 1 over x squared dx. Okay. Again, I would normally give you some time to think about this one, but 2 things are clues here that I need to do in a substitution. Notice I have a composition here, e to the something, so I'd be tempted to let u equal that something. And what you might notice, if you remember the derivative of 1 over x, is negative 1 over x squared. So the derivative of x to the minus 1 is negative x to the minus 2. So that is, this 1 over x squared part is actually my du. But I'm going to put that negative on the other side. And so this integral turns out to be e to the u, and then I've just got a negative du. So I pull that negative out, and the antiderivative of e to the u is e to the u, and I just sub in my u again. Okay. All right. Okay, last example here. Let's do the antiderivative from 0 to 1. Let's do the area under the function e to the x over 1 plus e to the x dx. Okay. And here, again, I don't know if I said this, but you'll notice that the top is actually the derivative of the bottom. That is almost always a clue that you want to let u equal the bottom. And then if the top is the derivative of the bottom, the top is going to end up being the du, and that's true here. Now the reason I want to do this problem is I want us to remember how to do this when we have a definite integral. So I'm going to get 1 over u, the e to the x dx becomes the du, and I'm going to substitute in when x is 0, e to the 0 is 1, u is going to be 2 there. Okay, again, when x is 0, e to the 0 is 1, so I get 2 there, and when x is 1, I get 1 plus e here. So now I don't have to go back to x's. I've substituted everything. And so then I'm going to get natural log of absolute value of u from 2 to 1 plus e. Everything's positive here, so you don't actually need absolute value. And I'm just going to sub in natural log of 1 plus e minus the natural log of 2. That is my answer. Whatever that is. We could plug it in a calculator and get an approximation to that. Okay. So all of the homework problems that you have from these sections, it looks like 5 sections. I think I've only assigned problems from 3 of them, 5.2, 5.4, and 5.5. You'll have some time today to work on those. You can also work on the numerical integration problems. Both of those are going to be due next week. And when we get back together next week, we will be looking at some integrals of inverse trig functions. Again, kind of reviewing some stuff that we've already seen. So the beginning of next week should not be anything really new either. One point that I just want to point out here kind of at the end is that when I first made that table, when we first explained these functions, we first developed a to the x, then we used that to develop e to the x, and then we used that to develop the natural log as an inverse, and then we used a to the x to develop the log base a function. But one of the things that you probably noticed right at the beginning when we were talking about this was that I did not have a very good definition for what this function a to the x actually means. One of the examples that I actually brought up when we first did this is 2 to the 1/2 means some number that when I take 2 copies of it, multiplied together I get 2, but I don't even know if such a number exists. Even worse, if I take 2 to some other number like square root of 2, I don't even have a meaning for this. So the way around that is to actually chuck this method completely. If I really want to make this rigorous, now we didn't make it rigorous, but we made it kind of more intuitive. If I really want to make it rigorous, what I can do is I can start with the natural log function. There's actually a formal definition for this, which I'll mention in a second. But then I can, from the natural log function, I can define e to the x as the inverse. And from e to the x, I can make a to the x. And I can also make log base a of x using kind of a log law that we're familiar with. So the question then becomes, how do we define this? Well, it turns out that you can define the natural log as the area from 1 to x under 1 over t dt. Now, this should remind you of something that we saw back in the fundamental theorem of calculus. This type of area function under 1 over t from 1 to x, you'll notice that this area function, if I call this a, that area function, when I differentiate it, the derivative is 1 over x, and that is what we're familiar with for natural log. So it turns out that you can define the natural log function as an area under this very easily understood function 1 over t. And then from that, you can get the e to the x, a to the x, and log base a of x functions. That's why the book's kind of reserving this to chapter 5 to try to do this development in all of its rigor. And if you actually read through the section, it'll start by talking about some of this. To me, that's not the greatest presentation of natural log right away when you're not very comfortable with natural log in the first place. But that's why it got reserved until chapter 5. We're not going to be doing anything with that here, but it's just more so you know that. Okay, that's it. You should have some extra time today to work on some homework problems. And so I will give you that. And you can ask Ms. Baribeau if you have any questions. Otherwise, have a great weekend, and I will see you on Monday. Take care.